Welcome to the third and final lecture from this Pythonic notebook. In this video, we will be talking about dealing with and interpreting error messages in Python. So, we've encountered many times in our notebooks errors illustrating ways in which code can go wrong, or the effects of various operations in Python, showing, not only the way things can go wrong, but also the way that Python is structured. And when we've got an error message, or if there is any code that the Python interpreter can't execute, it will raise what's called an exception. So an exception and an error are somewhat similar things, basically the same thing. Exceptions are deviations from expected behavior. So when normally we expect the interpreter to simply execute line after line after line in our code, and exceptions are deviations from that behavior, where the Python interpreter says, I don't know how to do this. It raises an exception. Often in our notebooks, and I've talked about this in office hours, there's a post on the several posts on the discussion board about it. So if you search for expect exception on the message board, you can find some posts about what that means. But basically, anytime you see this expect exception magic, it's just an indicator that we know this cell will raise an exception. And it helps us test these notebooks to make sure they're working correctly. So for example, if we try to add an integer to a string, we're going to get a type error. And we expect that because we know already that this will happen. If we do 2 plus 3 without the expect exception line, we see the exact same result. There's no difference here. But let's focus on what this exception tells us. It says type error, unsupported operand type, plus for int and string. Meaning we tried to add together an integer and a string, and the Python interpreter doesn't know how to add those things together. We can imagine several solutions. Whoops. We could imagine, for instance, 2 plus 3, where we should coerce the string into a number. We could also imagine something like this, where we coerce the number into a string, and we get a concatenation of the string 2 with the string 3. And these are two very different answers. So what should happen? Well, if we go back to the Zen of Python, we remember, in the face of ambiguity, refuse the temptation to guess. It's ambiguous how to interpret 2 plus, quote, 3. Should we interpret it this way? Or should we interpret it this way? It's not clear. Or maybe there are yet still more interpretations we could imagine that would be equally valid. So rather than guess what the user is trying to do, Python raises an exception and says, I don't know how to do this. It's not defined. Exceptions give us a lot of information. Already the name of the exception tells us something about what went wrong. Here we got a type error because the problem arose from the use of two types that had an incompatible definition for plus. Likewise, exceptions contain traceback that help us find where in the code something went wrong. And we will, as we'll discuss later, we can use this information to find parts of our code that are not working correctly, or that are raising these exceptions anyway, and investigate why they're appearing. Is it because the data looks differently than we expected? Is it because we have a typo? Is it because we simply used a name that doesn't exist, and we forgot that we were supposed to define that name somewhere else in our function? However, sometimes we expect certain exceptions and we want to catch them. And when an exception occurs, we want to deal with it in some special way. So let's decide, for instance, that we want this interpretation of addition, where we coerce any string into a number and then add it to whatever numbers we might have. So we can write an add function that accepts two variables, x and y, and tries to return their summation. If we encounter a problem, we'll catch the type error and make sure that both variables are cast as floats. And now, this will return 5 for 2 plus quote 3. Because when this line would have raised an exception, Python caught it and handled it. So this is called exception handling. It can be very useful, but I want to issue a word of caution. I've said other times that many students feel that error messages are a problem, and that if we could just get rid of the error messages, then our code would run and everything would be okay. Remember, exceptions is information from the interpreter that is something is not working as we would have expected it to. We shouldn't throw that information away unless we are very certain that we want to. Back to the Zen of Python, errors should never pass silently unless explicitly silenced. Here, we're explicitly silencing a type error by doing something to handle it. Now, some of this might still not work. If we try to add 2 to the letter E, we'll still get an exception. So we encountered a type error when we tried to return x plus y. So our exception handling caught it. During the handling of the above exception, another exception occurred. So as we were handling that type error, here in our exception handling, we raised another exception, could not convert string to float E. So this coercion, float, did not work on the letter E. So while we explicitly silenced a type error, we didn't silence all errors. So something to be careful about when when using try except is we should be specific about what kind of error we want to catch. If we define the exception too broadly, then we'll catch any exception, including those that we don't anticipate. And then we can get into a situation where errors are occurring, but we don't know about them. and this may cause our results to become erroneous or create other problems in our program. So you should never ever use a bare except, meaning we should never have this. We should always specify what kind of exception we're handling, and that exception should be as specific as possible. Another way to handle exceptions, as we have seen in the past, for instance with avoiding key errors with dictionaries, is to check if the conditions under which we expect an exception to arise are met. Here's another function, add2, which also accepts an x and a y for arguments. And instead of try except to handle the possible exception raised when adding two objects that are not both numbers, we check whether x is a number and whether y is a number. And if either one is not a number, we cast it as a float. And this also works. So which one should we choose? Try, except, or the if statements? These two patterns exemplify different approaches to the problem. This approach is sometimes called ask for forgiveness, not permission, meaning we don't ask for permission to add x to y, we just try it. And then if something goes wrong, we ask for forgiveness. We try to be a little more careful. This approach is sometimes known as look before you leap. Before we try to do anything with x and y, we first check whether they're the correct type, and if they're not, then we cast them as floats. So this is referred to as look before you leap. We ask for permission to avoid having to ask for forgiveness. In Python, the Pythonic style is ask for forgiveness, not permission. It's easier to ask for forgiveness than permission. In Python, usually the approach is to try something, and if it doesn't work, maybe we can handle the exception, maybe not. This has the effect of keeping code a little bit more straightforward. Under ideal conditions, this try simply works. In the other approach, I have to first think through like all of these conditional checks and maybe perform extra actions, and it's not even clear why I'm doing this until I get to the end of the function. Just like with comprehensions, the try except block reorders the presentation of what we're trying to do. We put the thing that we would like to do first, and that conceptually prioritizes our goals in the code. And that keeps things a little bit more readable and conceptually clear. Also, actually, this has the benefit of being faster. With look before you leap, we have to run these lines every single time we run the function, regardless of whether or not they're necessary. With this approach, most of the time we just run the try block, because the try block should work most of the time. As long as we're adding two numbers, we never run this part of the function. This part's very cheap. This part is expensive. So as long as we don't expect to encounter exceptions very often, this approach will be more efficient than this approach. but it depends on the idea that exceptions are exceptional, meaning that they happen infrequently. If we're encountering many exceptions, or if we're encountering exceptions most of the time we run this function, then that exception is not exceptional, and we'll be running this expensive exception handling code far too often. And it will become less efficient than this approach. Now let's talk a bit about debugging. So, I mentioned already that this error message contains a lot of information. It tells us something about why the error occurred and where the error occurred. But, for something simple like this, the traceback is not all that necessary. There's one line of code. There's only one place where the exception could have occurred. But as we deal with Python packages, often the traceback will get more complicated, and it's helpful to be able to view the full call stack of functions in order to get an idea of where the exception was raised, both at the top level where we interact with the code and at the very low levels where whatever elementary operation encountered a problem. So here we're going to try and create a pandas data frame, but we're going to do it incorrectly. We're going to have two columns. This first column will have the strings 1, 2, 3, and the second column will have one element, test. The columns of a data frame need the same number of elements, and so this is going to have a problem. We encounter a value error. And the traceback doesn't tell us a whole lot in this case, but the error message is rather useful. Shape of past values is 1 by 3. Indices imply 1 by 1. So here we had a problem where there was a mismatch in the shape of these two data structures for constructing the table. We'll see in the future more traceback where we'll want to trace through line by line how these function calls interact and why they might lead to a exception being raised. But it's crucial that we practice reading traceback and error messages to figure out why code is failing and try to find a solution. So here I see the shape of the past values is 1 by 3, but the indices imply 1 by 1. And that's telling me here, there's a mismatch between my indices and my values. So I'll just change this so my indices have the right dimensions, the right shape. And now I see my table was correctly created. So I'm going to conclude the lecture here and leave you with some exercises. Each one of these examples will fail for some reason. For example, here we encounter a type error. Float argument must be string or number, not list. I'd like for you to run each of these examples one by one, and once you find the error message, attempt to fix the example such that the code executes in a sensible way. So pause the video, work on those exercises, and then unpause and I'll share my solutions. Okay, So here we're trying to convert 1 into a float, but that 1 is inside of a list. Now there's a couple of different things we could do here. Since there's only one number, we might just be trying to convert the integer 1 into a float, 1.0. But we might also be trying to convert everything in the list into a float. What if we want to preserve that this is a list, but convert the numbers inside into a float? Then we might want to use a list comprehension. So now we have 1.0 inside of a list. For example 2, we encounter an index error. List index is out of range. We're trying to access the element at position 1 in the list, but there's nothing in the list, so there's nothing at position 1. Even if we try position 0, that will also fail because the list is empty. Presumably here, the most sensible thing to do is to simply have items in our list. If we were trying to select an item at a particular position, probably we don't intend for this list to be empty. And the final example I already solved. I just need to make the length of my index match the length of my values. So that concludes the lecture on Pythonic style and Pythonic programming. And the next set of videos we'll be talking about we'll be all done with the Python module, and we're going to move over to data wrangling to talk about input-output.